Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 6. Aitken's and Steffensen's Acceleration Methods. From a given convergent sequence, one can build several iterative schemes that converge faster towards the same point. This process, known as acceleration, has found an application in the root-finding algorithms. Accelerating the convergence of root-finding methods is crucial for improving the efficiency of algorithms, especially when dealing with problems that require high precision or when iterating over large datasets. A root-finding method may require acceleration when it exhibits slow convergence. Methods like the bisection or secant methods converge linearly, which can require too many iterations to reach a satisfactory level of precision. Difficult function behavior. Some functions may exhibit sharp gradients, oscillations, or high curvature near the root, making standard methods to converge slowly or even diverge. Multiple roots in close proximity. If a function has several roots in a small region, a method may converge to one root but struggle with others. Accelerating convergence can help explore all roots more efficiently. The Aitken's delta-squared acceleration technique is one of several that suit this purpose. This technique transforms an original sequence, XP, into another sequence that converges with fewer iterations, faster, to the answer than the original sequence. Consider the sequence, X, that converges to alpha. The formula for the Aitken's delta-squared process yields the following, which generates alpha p using x, p minus 1, xp, and x, p plus 1. The advantages of the Aitken's method are: the method does not depend on the kind of root-finding method used to generate a sequence. It is not confined to sequences obtained by root-finding methods, but can also be applied to convergent series. The disadvantages of the Aitken's method are: its convergence is rather slow. Computation of the differences, delta xp and del squared xp, can lead to loss of significance. An original sequence should have a sufficient number of terms. Otherwise, the acceleration procedure may lead to divergence or, at worst, give a solution that is grossly in error. Consider the following nonlinear equation. Find its root using the fixed-point iteration method with the Aitken's acceleration technique. Use 1 as the initial guess and 5 times 10 to the minus 5 as the absolute convergence criterion. A sequence of estimates will be obtained using the fixed-point iteration method. We use the following form of the fixed-point iteration equation, which was found to converge in Section 4, Video 3. Using the initial guess value of 1, we find a new estimate x1. Next, using x1, we calculate the second estimate x2. Subsequently, x3 and x4 are calculated in the manner using the prior estimates. Now, we calculate the differences between the two consecutive iterates. The difference between x1 and x0 is found as 0.362761. The difference between x2 and x1 is obtained as 0.020415. The difference between x3 and x2 is calculated as follows. And finally, we calculate the difference between x4 and x3 as follows. The first estimate of the new sequence, alpha 1, requires delta x1 and delta x2 along with x2. Alpha 1 is found as 1.38, 43, 936. The next iterate, alpha 2, requires delta x2 and delta x3 along with x3, which yields 1.38, 43, 541. And finally, alpha 3 is calculated using delta x3, delta x4, and x4. The difference between the consecutive alphas are found as follows. Delta alpha 2 is in the order of 10 to the minus 5, which is also smaller than the prescribed convergence tolerance. Hence, at this point, we can terminate the iteration process and settle with alpha 2. However, let us also calculate delta alpha 3, since we already have alpha 3 at hand. Delta alpha 3 is in the order of 10 to the minus 7, which implies that alpha 3 yields an estimate that is accurate to at least 6 decimal places. Steffensen's acceleration is another iterative root-finding technique that is a combination of fixed-point iteration and Aitken's acceleration method. It offers accelerated convergence for sequences that converge to a solution linearly and has a quadratic convergence property for well-behaved functions, meaning that the number of correct digits roughly doubles with each iteration once it is close to the root. The motivation behind this technique is that alpha p of the new sequence estimate is a better approximation to the fixed point estimate xp plus 1, so it is used as the next iterate for the fixed point iteration process, i.e., the improved estimates are used in the fixed point iteration equations as soon as they become available. The Steffensen's algorithm starts with an initial guess, alpha 0. This guess is set to x0. x1 and x2 are computed using the fixed point iteration equation. Then, the first iterate of the new sequence, alpha 1, is calculated using x0, x1, and x2. A convergence check is performed based on the absolute difference of the alphas, or the absolute value of alpha 1 minus f alpha 1. Or both. If alpha 1 satisfies the convergence criteria, the procedure is terminated. Otherwise, alpha 1 is set to x1, and x2 and x3 are calculated using the fixed point iteration equation. Alpha 2 can now be calculated using x1, x2, and x3. Likewise, the convergence test for alpha 2 is carried out in the same fashion. This procedure is repeated until alpha converges to an estimate within a tolerance. The advantages of the Steffensen's method are: the method has a quadratic convergence rate. It does convert diverging iterations into a converging sequence. Unlike Newton's methods, it does not require the first or second derivatives, which provides a considerable advantage in cases where a derivative is not easy to evaluate. The disadvantages of the Steffensen's method are: the cost of faster convergence comes as a result of two function evaluations, namely evaluating g for the prior and current estimates per iteration step, which increases the CPU time. The convergence behavior depends on the iteration function and the proximity of the initial guess to the true value. The method may fail to converge, or the sequence of estimates may either oscillate about the true value or diverge if the initial guess is not sufficiently proximate to the true root. It is difficult to extend to multivariable nonlinear systems of equations. Let us tackle the same example problem using the initial guess value of alpha 0 equals 1, which is also set to x0. The estimates x1 and x2 are obtained using the fixed point iteration equation. Having x0, x1, and x2, we can calculate delta x1, delta x2, and delta squared x2. For delta x1, we find 0.362761. For delta x2, we obtain 0.020416. For delta squared x2, we find minus 0.342345. Using x2, delta x2, and delta squared x2, we can calculate the first estimate for alpha as follows. Alpha 1 yields 1.3843,936. Next, we set alpha 1 as x1 and calculate x2 and x3 using the fixed point iteration equation. Then, the first and second differences are calculated as shown. Using x3, delta x3, and delta squared x3, we calculate alpha 2 as follows. We notice that the differences become small very quickly. Since the absolute difference between the alphas satisfies the convergence criterion, we may terminate the iteration process. We observed that this Steffensen's technique converged to an approximate solution very quickly. That is all for now. See you next time with another topic. Bye.